If someone asked you to picture a quantum computer, what would you see in your mind? Maybe you would see a normal computer, just bigger with some mysterious physics magic going on the inside. Forget laptops or desktops, forget computer server farms. A quantum computer is fundamentally different in both the way it looks and, more importantly, in the way it processes information. There are currently several ways to build a quantum computer, but let's start by describing one of the leading designs to help explain how it works. Imagine a light bulb filament hanging upside down, but it's the most complicated light you've ever seen. Instead of one slender twist of wire, it has organized silvery swarms of them, neatly braided around a core. They are arranged in layers that narrow as you move down. Golden plates separate the structure into sections. The outer part of this vessel is called the chandelier. It's a supercharged refrigerator that uses a special liquefied helium mix to cool the computer's quantum chip down to near absolute zero. That's the coldest temperature theoretically possible. At such low temperatures, the tiny superconducting circuits in the chip take on their quantum properties. And it's those properties, as we'll soon see, that could be harnessed to perform computational tasks that would be practically impossible on a classical computer. Traditional computer processors work in binary. The billions of transistors that handle information on your laptop or smartphone are either on, 1, or they're off, 0. Using a series of circuits called gates, computers perform logical operations based on the state of those switches. Classical computers are designed to follow specific, inflexible rules. This makes them extremely reliable, but it also makes them ill-suited for solving certain kinds of problems, in particular problems where you're trying to find a needle in a haystack. This is where quantum computers shine. If you think of a computer solving a problem as a mouse running through a maze, a classical computer finds its way through by trying every path until it reaches the end. What if, instead of solving the maze through trial and error, you can consider all possible routes simultaneously? Quantum computers do this by substituting the binary bits of classical computing with something called qubits. Qubits operate according to the mysterious laws of quantum mechanics, the theory that physics works differently at the atomic and subatomic scale. The classic way to demonstrate quantum mechanics is by shining a light through a barrier with two slits. Some light goes through the top slit, some the bottom, and the light waves knock into each other to create an interference pattern. But now dim the light until you're firing only individual photons one by one. These are the elementary particles that comprise light. Logically, each photon has to travel through a single slit, and they've got nothing to interfere with. But somehow, you still end up with an interference pattern. Here's what happens according to quantum mechanics. Until you detect them on the screen, each photon exists in a state called superposition. It's as though it's traveling all possible paths at once. That is until the superposition state collapses under observation to reveal a single point on the screen. Qubits use this ability to do very efficient calculations. For the maze example, the superposition state would contain all the possible routes, and then you'd have to collapse the state of superposition to reveal the likeliest path to the cheese. Just like you add more transistors to extend the capabilities of your classical computer, you add more qubits to create a more powerful quantum computer. Thanks to a quantum mechanical property called entanglement, scientists can push multiple qubits into the same state, even if the qubits aren't in contact with each other. And while individual qubits exist in a superposition of two states, this increases exponentially as you entangle more qubits with each other. So a 2-qubit system stores 4 possible values, a 20-qubit system more than 1,000,000. So what does that mean for computing power? It helps to think about applying quantum computing to a real-world problem, the one of prime numbers. A prime number is a natural number greater than 1 that can only be divided evenly by itself or 1. While it's easy to multiply small numbers into giant ones, it's much harder to go the reverse direction. You can't just look at a number and tell its factors. This is the basis for one of the most popular forms of data encryption called RSA. You can only decrypt RSA security by factoring the product of 2 prime numbers. Each prime factor is typically hundreds of digits long, and they serve as unique keys to a problem that's effectively unsolvable without knowing the answers in advance. In 1995, MIT mathematician Peter Shor, then at AT&T Bell Laboratories, devised a novel algorithm for factoring prime numbers, whatever the size. One day, a quantum computer could use its computational power and Shor's algorithm to hack everything from your bank records to your personal files. In 2001,